Hi, I'm Borna, your organic chemistry tutor, and in this video I'm going to show you guys how to decide what side an acid-base reaction is going to favor. Well, when I was learning this subject, it was a little hard on me, and also my students were having trouble with it, so I just decided to make a YouTube video about it. Stay tuned until the end of the video. I'm going to give you guys some estimated pKa values to remember that is going to help you a lot, trust me. Let's get started. Alright, so let's begin our discussion by discussing a typical acid-base reaction. Here we have acetic acid reacting with ammonia to give us ammonium acetate. An acid-base reaction is a reaction in which a proton is being transferred from one species to another. This proton is going from acetic acid to ammonia to give us NH4 plus and OAC minus, which is this thing. Our acid is the donor of the proton. Our base is acceptor of the proton. So, on the left side of the reaction, acetic acid is our acid, ammonia is our base. However, very interestingly, when something donates a proton, when an acid donates a proton, it becomes a base because it can accept that proton. I'm not talking about how willing it will be to accept that proton, but that is technically possible. That is why each acid is going to have a conjugate base, and each base is going to have a conjugate acid. Acetate we refer to as the conjugate base of acetic acid. Ammonia is the conjugate acid of NH3 ammonia. Alright, now how do I decide which direction this acid-base reaction favors? Because this is an acid-base reaction going from left to right, and it's an acid-base reaction going from right to left, and it's an equilibrium reaction. How do I know which direction of the equilibrium is favored by the reaction? Well, the reaction favors stability. And stability lies with weaker acid and base. So the reaction is going to favor the weaker acid and weaker base. Interestingly enough, the weaker acid and the weaker base have to be on the same side of the reaction. I'm going to explain why and how. Alright, first of all, let's find the weaker acid and the weaker base. I'm gonna erase the definitions just to make up some room. On the left side of the reaction, my acid is acetic acid. On the right side of the reaction, my acid is ammonia. Acetic acid has roughly a pKa of close to 5. Ammonia has a pKa of close to 9, 10, something in that neighborhood, meaning that my weaker acid is going to be ammonia. And actually, comparing the basicity of acetate to NH3, because acetate is the conjugate base of the stronger acid, it has to be the weaker base of the two of them. So comparing acetate to ammonia, this is going to have to be the weaker base. Ammonia has to be the stronger base. So stronger acid and stronger base always have to be on the same side because the weaker base comes with the strongest acid or the stronger acid, so it has to be on the same side as the weaker acid. And the weaker acid and the weaker base always are going to be on the same side of the reaction. So this particular reaction is going to favor the right side. Now let's apply that principle to a different reaction. What if I was reacting a terminal alkyne, say acetylene, with butyl lithium to give me butane and acetylide? Well, let's see. The acid on the left is going to be acetylene because that is what is losing the proton, and that proton is going to be installed on butyl. So that is my base on the left. The base goes to its corresponding conjugate acid, so let me say Ca of the base for conjugate acid of the base. Ca of base. The pKa of this thing is very, very high. It's like difficult to measure. It's an alkene, so I'm going to say it has a pKa of around 50. And then this is going to be Cb of acid. And my acid on the left has a pKa of around 25. So the weaker acid is actually right here. And this is the weaker base because it's the conjugate base of the stronger acid. So the weaker acid and the weaker base are on the right side of the reaction, so this reaction is going to favor this side. Alright, now I'm going to give you some pKa values. I know that you're told you don't have to memorize them. I know that you're going to be given a table, all that stuff. But trust me, knowing the different pKa values of things is going to give you an understanding, is going to let you compare different things in terms of their acidity. I know that you don't need to know exact numbers, and that's why I'm not giving you exact numbers. I'm just giving you some estimations, and I think these values are very, very helpful to remember, trust me. An alkane is going to have a pKa of around 50. That's probably the most unacidic thing you're going to be dealing with. Alkene, a little more acidic at a pKa of around 40-45, so 45 is a good value to remember. And a terminal alkyne is going to have a pKa of 25, so that's the most acidic of them all. Now, let's go to some oxygen-based acids. H3O plus has a pKa of -2, so if I'm asked to compare the acidity of, say, an ROH2 to something, well, this is not going to be on table, most likely, so I just estimate that the pKa of that is going to be close to that of H3O+. I'm going to say that it's probably close to -2, because that R group does affect acidity, but not by much. That's why I think this is a good value to remember. Water and most of the alcohols are going to have a pKa of around 17. Your typical alcohol, your typical carboxylic acids is going to have, or are going to have, a pKa of around 5. NH3 going to RNH3 plus going to RNH2 is going to have a pKa of around 10, but RNH2 going to RNH minus, obviously is going to have a much bigger pKa around 35. These are two very helpful values to remember. And then some random ones. H2 is going to have a pKa of around 35. That's helpful to know because sodium hydride, NaH, or potassium hydride, those are pretty common bases. So knowing that value is going to help. Your typical RSH, your typical thiol, is going to have a pKa of around 10. Also, same thing for your typical phenol. And as you can see, your typical phenol is a little more acidic than your typical alcohol because your OH is connected to an aromatic ring. And that's all. Alright, I hope you guys liked this video. If you did, please give it a thumbs up. That's going to help me a lot. Also consider subscribing to my channel to see more tips and tricks, tutorials, and solved problems. Check out my website at yourokchemtutor.com, and I'll see you in the next video. Take care.